X-ray spectroscopy and imaging. These are observatory class, not focused to a specific science. Okay. Athena, however, for the first time we will open up the possibility of looking at warm-heart intergalactic material, but with limited sensitivity. Then in the coming years, niche area, instruments that will look at some niche area. One is GRISM. This is the follow-up of the Hitomi mission, which failed because of a spacecraft failure after after a few days of operation in space. Then we have POLIX that we are working on, which is dedicated polarimeter instrument in a narrow band of 8 to 30 keV. Then there are proposals of various kinds. For example, Daksha, which is an all-sky instrument to look at gamma ray burst in the sky and possibly gravitational wave events, their electromagnetic counterparts. Okay, and there are proposals of many different proposals towards looking for warm-heart intergalactic material, which is basically looking at oxygen lines. Okay, this requires relatively wide field of view and extremely high energy resolution. For example, looking for various oxygen lines, oxygen 7, oxygen 8, and so on, probing different temperatures in the filaments, the large-scale structures. EXTP also falls in a class of observatory where we basically have a collection of large number of instruments of various kinds, close to the base of that time. And Daksha also falls in the all-sky category. So now if we talk about small satellite mission, okay, small satellite mission has to find a niche area because small satellite mission would not give you anything that is comparable to the large-scale missions, okay, even in a narrow energy band or in terms of spectral resolution, in terms of angular resolution or anything. Okay. So anything that you look for in few hundred kg class satellite of the order of 100 kg class scientific payload, one has to find a niche area in terms of science. So I try to motivate towards that. One niche area for smallish class satellite is broadband X-ray polarimetry. Okay, this is a proposal that we had worked together a few years ago. However, one key development for this is hard X-ray optics. Okay, and Vikram later today will talk about initiatives towards hard X-ray optics development, which has to be understood. But prior to that, if we talk about the small satellite science program, with the technical capabilities that exist in the country, these few options are being considered. Okay, one is soft X-ray polarimeter. The polarimeter that has been launched by NASA is an imaging polarimeter. Okay, the very construct of these devices, you have very limited effective area, especially at energy above 5 kV. Okay, so this instrument, even though it's an imaging polarimeter, its effective area is very limited as you go to slightly higher energy band. What is being considered here is a soft X-ray polarimeter with a slightly different configuration of the instrument, which will give you larger effective area, okay, at the cost of imaging. So this would be a polarimeter where you would not have imaging, but you would have slightly larger effective area, or factor of a few larger effective area compared to the NASA mission IXP. Another possibility that is being considered is instead of soft X-ray polarimeter, one can go for hard X-ray polarimeter, but without the hard X-ray optics.
At time.
Okay, is hard X-ray polarimeter but without any optics. This will have limited sensitivity, but at the same time in the coming years, 5 to 10 years, there is no hard X-ray polarimeter mission envisaged. So the current soft X-ray polarimeter of NASA, the medium energy polarimeter that we are launching along with an hard X-ray polarimeter would give a broad enough coverage even though with limited sensitivity. So this is one thing that is being considered. One other instrument that is being considered is on POLIX we have an instrument in addition to POLIX which has a very small effective area, okay, in the soft X-ray band. Currently it's planned to look at the POLIX sources. Simultaneously. Okay. We are considering increasing the scope of that instrument, okay, by filling up the entire satellite deck of an instrument with the entire satellite deck with same kind of instrument, thereby increasing the effective area. So I would primarily be discussing if we have a much larger effective area compared to what is being flown along with POLIX, what is the science prospect of that? Okay. This is soft X-ray spectroscopy with large area detectors. And another thing that is being considered is slight variation of this, where you will have a concentrator optics, okay, and that will help us widen the energy band of this instrument. Okay, this is somewhat similar to the NICER instrument on board International Space Station. So these are the 4 things currently being considered among various instrument groups within the country. We would probably come up with a proposal which can then be put forward to ISRO for further consideration. So these POLIX which we are currently working on POLIX we have, in addition to the POLIX instrument which is at the center, these detectors expect there is one pair on this side, another pair on that side. These are very small instruments with 16 square centimeter for each tower, so total 64 square centimeter on the satellite. The idea is to, so this is a blown up view of the same instrument. What you have is the actual detector area on that whole platform is a very small fraction. This is just 16 square centimeter over a rather large radiator plate. Okay, so currently our consideration is primarily to cut away or reduce the dead area on this. Okay, compactify the whole thing so that your effective area of the instrument to the total footprint increases, thereby giving us some international compactification. So we looked into the ways this can be compactified, and it looks like we can have an instrument which is as large as 36 times what is being currently flown along with POLIX. Okay, here we have a 6x6 arrangement of these units, and 4 such instruments can be put on the entire satellite tail. That would give us an effective area. This is the effective area curve for this instrument shown in red compared to the effective area of XMM Newton PN detector and the NICER instrument on board International Space Station. Okay. So we have a significantly larger effective area, larger by a factor of 2 to 3, or in this like around 6 kV it is even larger compared to XMM Newton and NICER, and that gives us an discovery space or certain topics we will have better access if we try to address a couple of those. We are also considering increasing the effective area at lower energy by modifying the filter that is used on this. This effective area falls from here to down at lower energy band below 4 kV because of a certain kind of filter used. By optimizing the filter, it may be possible to increase the effective area even more. So this instrument is particularly good if you compare with XMM Newton or NICER in this energy band 4 to about 10 kV. Okay. Of particular interest in this band is the iron line, which is very common in X-ray binaries, and we often try to use the iron line for different kinds of probes and struggle while using data even from XMM Newton, okay, which is one of the largest. And why is iron line so important? Certain kind of sources that we study are, for example, these high mass X-ray binaries, where you have a high mass star around which there is a neutron star. It can either go around in a circular orbit or a largely elliptical orbit. The structures in the wind of this companion can be probed by looking at the reprocessing of the X-rays which are produced on the neutron star. The neutron star X-rays come to us directly. The same X-rays get reprocessed in this entire environment and come to us in the form of an absorbed X-ray spectrum at low energies and an iron emission line. The iron emission line, depending on where it is produced and depending on the ionization state of the material, can be 6.4 kV, which is mostly from neutral iron, or hydrogen-like iron, or helium-like iron, and so on and so forth. Okay. That requires modest spectral resolution that we will have on this instrument, and that requires extremely large effective area, even larger than XMM. So I'll quickly take you through one example. There are many sources and many different science cases. For sake of time, I'll just take you through one. This is the famous source, GX301-2. This source has an orbital period of about 32 days, and in this period, the X-ray intensity modulates by a large factor. Okay, and this modulation is extremely stable. Most interesting thing is, from the pulse arrival time, this is pulsar 2, from the pulse arrival time, we know the orbit of this neutron star around the companion, except for its inclination with respect to our line of sight. And we know which direction we are looking at. We are looking at this source from this direction, if this is the orbit. The funny thing that happens is the peak of this X-ray intensity is not when the neutron star is closest to the companion or when the neutron star is slightly past the companion. You would have expected the mass accretion would be highest when the neutron star is closest to the companion, if it was a isotropically outflowing wind from the companion. Okay. Instead, the peak comes at phase about 0.1, 0.15 earlier than the closest approach. Okay. So one model that was given for this is that the companion star can have an outflowing wind. We have these B stars which are rapidly rotating and they have an equatorial outflowing disk. And the disk is of such an extent that when the neutron star is passing at this end, it intersects the disk and thereby causes absorption. It causes accretion of material which causes this flare. And after this, when it is passing through the other end, it probably does not encounter as much material, so the second peak is not as prominent. Okay. Overall, this explains the light curve. Another model for this light curve is as this neutron star goes very close to the companion is a massive and extremely large size star, it probably draws out material from the surface of the companion, and that drawn out material flows in the form of a stream. Okay, and as this neutron star is cutting this stream in this phase, okay, that causes the flare. And either of these models give you a model for what should be the column density of absorption by the same material that is causing the enhancement in accretion. And if that was true, we would have this kind of modulation in the absorption column density given by this dashed curve here or given by these stars. These are two different models. Okay. The observed data, which was there in the previous slide, actually does not support either of these. Okay. That's one thing. The absorption column density does not match with what was expected from the given models. Plus, we looked at this source using data from an instrument which was not meant for this kind of study, the all-sky monitor on board, 2 minutes, yeah. The all-sky monitor on board International Space Station. Okay, using data acquired over about 15 years in a unique way. Oh no, when we analyzed this was about 5 years old. In a unique way, we measured the absorption column density as a function of orbital phase. And to remind you, for a 40 days orbit, there is no other way of measuring the absorption column density because no observatory is going to give you a 40-day long exposure to a given source. Okay. What was most interesting was that at a particular phase of about 0.15 or so, what you find is that there is a large equivalent width of the iron line. There is a huge iron line, similar to like what you see here. Okay. This is an XMM data. Even when there is no absorption column density. Okay. The source is not causing absorption to us, but there is a huge increase in the iron line which is getting produced, an extremely strong iron line with an equivalent width of about 1.5 keV. Okay. So what causes the production of this iron line? Only possibility is that if there is an stream or an accretion curtain or something behind the star. There is a neutron star which is causing radiation, but there is a reprocessing material window or curtain behind. These kind of studies we will be able to do far better if we could measure the spectra of these sources in a short interval. Okay. Then there are other X-ray binaries where you have outflowing wind, extremely clumpy. So when the neutron star goes through such a clump, you see very large absorption and associated increase in accretion column density and associated increase in equivalent width of the iron line. Or sometimes you see large absorption, no iron line, or low absorption, huge iron line. So these are all ways to probe the clumpy nature of wind of high mass X-ray binaries or winds of massive stars. But we are limited by, when you want to study of these subjects, our ability to measure spectrum in a short interval of time. All of these can be done if you can measure the spectrum in a short interval of time. One other object of study is, for example, this gravitationally redshifted iron line which is seen in AGNs, which is seen in galactic black hole sources, which is seen in neutron star sources. Okay. But these sources are so highly variable. The interplay between the corona that produces the hard X-ray continuum, the accretion disk where the hard X-ray continuum gets reprocessed to produce the gravitationally redshifted line, the interplay between these you can study, and these sources are extremely highly variable. Some of these sources can be extremely highly variable, that your interest lies in doing these measurements at short intervals of time. And short interval of time is where the difficulty is, because when you want to study this kind of, this is the last slide. When you want to study this kind of sources with an XMM Newton kind of observatory, currently that is the best one. Okay. The problem here is that XMM Newton for extremely bright sources will get piled up. Within one readout interval, if more than one photon falls, okay, the spectrum gets piled up. Okay. So pile up limits your ability to study these sources. Plus, for a given effective area and for a given flux of a source, if you want to improve sensitivity, you have to integrate it for longer and longer time. Okay, the T has to be increased. But the entire science case that we are talking about is motivated by measurements of these things in a short interval of time. If you could measure the spectrum of these sources with good statistics in 100 to 1000 seconds kind of time scale, okay, you would be able to address certain science that is not possible today. So that's the advantage of going into a large area detector. Even though this being an open detector, it will have large background, there are sources and there are time intervals. Okay, there are some bright sources where you need to make certain studies at a short time interval. Okay, to do that, you need very large area instrument. Okay, so this instrument around 6.4 keV R-line energy band, this is factor of like 4 to 5 larger than the current largest X-ray observatory. This of course doesn't include instruments like Astrosat. Astrosat also has very large effective area and associated large background. The difficulty here is that Astrosat, for example, large area X-ray proportional counter, being a proportional counter, has limited energy resolution. Okay, this has an energy resolution about 1 to 1.2 keV or 1.5 keV compared to a swept charge device that will be used here, which has an energy resolution in the ballpark of 150 to 180 electron volt. Okay, which is adequate for you to separate the 6.4 kV line, the 6.7 kV hydrogen lag line, helium lag line, 6.95 kV hydrogen lag line, and if you have in certain cases a Compton recoil component. Okay, the 6.4 kV line sometimes shows up as a Compton recoil component at a slightly lower energy. All of this can be probed with the spectral resolution that such an instrument can have. This will have large background, which will limit your ability to study sources only to brighter than about 20 to 50 millicrab. But there is a definite window for measuring spectrum at short intervals, okay, that only this instrument can provide because of its much larger effective area. So this is a niche area to be pursued with a small satellite instrument on like 100 kg, 140 kg kind of payload on a 400, 500 kg kind of satellite, and can be extremely competitive in its system. Thank you.
Time for some questions.
So what is the factor? The one that you're proposing can measure spectra at shorter time.
Short interval time scale.
Compared to XMM Newton, for example, what is the factor in terms of time?
So XMM Newton, you can see that the effective area at 6.4 kV is factor of 4 to 5 smaller.
It will be similar in time.
No, we need to measure the spectrum at a short interval of time. XMM Newton or Chandra, the signal to noise ratio, if you want to go higher and higher signal to noise ratio, you have to either go for, let's say, large bright sources, effective area is given, okay, or you integrate it for a long time. Since the science case is such that we have to make this measurement at a short time interval of 100 seconds or 1000 seconds, actually Chandra or XMM Newton is not so bright, not so good. For example, Chandra has such high sensitivity, but can you measure the pulse profile of an X-ray pulsar, a moderately bright X-ray pulsar, in 100 seconds? No. 100 seconds you simply do not connect enough photons. So if you need to do a spectral analysis of a spectrum with a 20 sigma significance to be able to measure the iron line with certain signal to noise ratio, then with Chandra X-ray observatory your integration time will be large. Okay? And in that integration time, the kind of variation that we are looking for gets smeared out. So the high sensitivity of Chandra and XMM, if you want to avail, you actually have to integrate for a long time. Polix early next year. Polix, the flight model fabrication is going on. We have technical issue on one aspect of the proportional counter detector that is currently being resolved. And Polix electronics is nearly done, the entire flight electronics.
So when you have ATM, then the idle line comes from that reprocessing by the corona and all those things.
No, reprocessing is from the accretion disk.
Oh.
Reprocessing from the accretion disk. You want to study the interplay between the corona and the accretion disk.
So when you have the X-ray binary, you just have the neutral star and the massive star. So what is the mechanism there?
The same thing. You have in black hole sources or low mass X-ray binary neutron stars in certain spectral states, you have the same thing. There is an accretion disk, there is a corona. The corona causes production of the, by compton upscattering the hard X-ray photons. Those hard X-ray photons get reprocessed in the accretion disk to produce the iron line and also the reflection bump in the spectrum.
So then the neutron star also has an accretion.
Neutron star, if it is a low magnetic field neutron star, then you can have accretion disk going very close to the surface where it can still show the same relativistic effect, the gravitational redshift of the iron emission line. This is seen in neutron star X-ray band is also, provided the neutron star has a low magnetic field string. So neutron stars, galactic neutron stars, galactic black hole binaries and AGNs, the production of these gravitational redshifted iron line is identical. What one doesn't know is that the role the corona plays, the relative importance that the corona has and its size with respect to the accretion disk, how quickly these things vary and so on. And to understand that, you need these measurements at short time scales. Okay. Thanks.
Our next speaker is Rajorshi Chandra. Our next speaker is Rajorshi Chandra, and he will speak on primordial power spectrum reconstruction for CMB replacement.
Hi, I'm Rajorshi, and so my talk will be basically about the primordial power spectrum reconstruction from the CMB weak lensing perspective from CMB power spectrum data. And so I recently submitted my thesis at IUCAA, and this work was done with my supervisor, Tarun Sharadeep. So this work is based on these two projects. First one is the primordial power spectrum reconstruction from CMB weak lensing power spectrum. And the second one is from this, the paper, primordial power spectrum reconstruction from CMB temperature power spectrum with iterative lensing accommodation or iterative delensing. So this is a brief overview. I'll give the introduction, a brief CMB introduction, the weak lensing physics, our technique, and the results from the two projects, and the conclusion. So this is the CMB temperature anisotropy map from Planck. So we assume that it is statistically isotropic, the underlying model assumption, and it's Gaussian distributed. And this is the two-point correlation function, or the power, CLTT power spectrum of the temperature anisotropy map from Planck. And this is the lensing potential map. This is also obtained from Planck, and we assume the same assumptions that it is statistically isotropic and Gaussian distributed. This is the consequent two-point correlation function obtained from multiple different experiments. We call this the CL55 or CL kappa kappa. So this is just a cartoon of the underlying lensing, the lensing phenomena. So the photons from the CMB temperature photons from the surface of last scattering are lensed by the underlying universe's matter distribution as it travels through time and reaches us at observation. So this is the weak lensing expression of how weak lensing alters the temperature anisotropy power spectrum. So it basically redistributes power and damps the peaks and the valleys in the temperature power spectrum given by this expression, where CL55 I showed earlier is the lensing power spectrum, and this is the unlensed temperature power spectrum, and this is the lensed temperature power spectrum. The SA and SB are basically geometric terms which are a function of the harmonic L indices and the Wigner 3J symbols. So this is the expression that we'll be working with. Now, generally, the temperature, the power spectra, the temperature or the lensing power spectra can be modeled as a convolution of the underlying primordial power spectrum, the original seed fluctuations, convolved with some radiative transport kernel, which contains the rest of the evolving physics, as the universe evolves. And the temperature and lensing power spectrum can be written in this form. Now, generally, PK is modeled in the lambda CDM model. It is modeled as a power law with 2 parameters. But that is again model dependent. So you can, of course, like what Planck, etc., do is that they try to get they try to constrain the parameters of the power law. But if you also want to, there are many other models, for example, in different inflation models that you can use. So you might want to do a free-form reconstruction of the PK, and this is what our goal is. So here, each P of K is considered, is taken as a free variable, and the number of free variables depend on how many samples you take of PK. And this basically becomes a deconvolution problem. Given this data and given the rest of the physics models in GLK, then you get PK. Now, what lensing does, if we put these equations back into the lensing expression, what we get, the lensed GLK we get is given in this form, and now you see the GLK itself has become a function of PK. Right? So this is a challenge. Now, for the simple case where CL is a function of PK, the method we use for deconvolution is the Richardson-Lucy reconstruction given by this expression. So you start with some initial guess of PK, and it's an iterative reconstruction, and this is your normalized GLK transport kernel. This is your data, and this is the iterated CL reconstructed from the previous PK version given by this expression. So you solve this iteratively and you converge to your estimate of PK given the data. Now what we do to address the previous challenge where GLK itself is a function of PK is we put this iterative correction term in the GLK, which is used in the estimate, and this iterative correction is based on the previous reconstructed PK, the previous reconstruction of PK. So the hope is that this iterative correction added to the kernel will help you converge to the accurate PK over multiple iterations. So here we provide a visual representation of the radiative transport kernels for this is for lensing. So this GLK is parameterized over L, in different colors and color gradients, and plotted on the x-axis is K, and this is the value of the GLK. So you see it's quite smooth over K. This is the PK, the range of K over which we'll be reconstructing PK, and this is the temperature kernel. So this is much more, much more high fidelity. The kernel is spiky. So now we move on to results based on this background information. So this is from the first project where so this is all done on simulated data. So here we simulate the CL55, which I mentioned earlier, the lensing potential power spectrum using a power law model. So this has not been done before. That this CL55 is not used to get a free-form PK. It has been done earlier on CLTT by other, by other authors before. So this is on CL55. So based on a power law simulated data with some realization noise added, which is limited by cosmic variance limited error bars, we get the PK reconstruction. So the orange is the input power law, and the blue and green are the PKs that we reconstruct. And these bands are the error bars that we obtain from generating multiple samples of the input data. So as you can see, within the error bars, we can reconstruct the power law, free-form power law model from this data. So given that in the already Planck has given pretty good, Planck, SPT, and ACT, and such missions have given good reconstructions on CL55. So this is a new avenue of data, that is a CL55 data that can be used to get a handle on the PK independent of the temperature power spectrum. And with future missions, we only expect the CL55 estimations to get better with better precision. So it's worthwhile to have this kind of this reconstruction methodology ready. We also implement a sparsity algorithm in which, based on the GL55 kernel that I showed earlier, the smooth one, this kernel, we can actually reduce the number of free parameters in PK, that is, reduce the number of PK samples. So this reduces the number of unknowns and degeneracies in the results, while keeping the fidelity of the reconstruction intact, which is shown here. The green one is the dense reconstruction, and the blue dots are the ones with the sparsity algorithm implemented. The advantage of this algorithm is that you can now get the full covariance matrix of the PK reconstruction, which can allow you to better constrain any features you may or may not find in the reconstruction that is deviating from power law. So this is the covariance matrix of the PK reconstruction obtained earlier, and the correlation matrix. Now we move on to the second part, where we want to get the PK while addressing for the lensing noise that is, or the lensing problem that is introduced in the CLTT. So this has been, in earlier work and literature, what has been done generally to address this lensing problem is that a power law based template of the lensing contribution was subtracted from the lensed temperature power spectrum data. Now the problem with this, the issue with this is that you're assuming a power law to remove the template, but your goal is to get the PK without assuming a power law. So it can bias your results, and so that is what we show does happen. And by doing the iterative correction where you don't assume any kind of template, you can get a better reconstruction of PK. So to illustrate this, we take a hypothetical feature for testing. So this is the power law for reference orange, but what we'll be doing, we'll be generating a primordial power spectrum with this bump-like feature in blue. So blue is our input, and we generate the CLTT and CL55 and the lensed CLTT simulated data based on this feature. So as you can see, the CL55, this is how this addition and bump changes the data. It moves up slightly. There's the relative difference between the two, the power law versus the feature. And this is how the CLTT changes. So here if you look closely, this is for the power law model, the dashed one, and this is for the one with the feature. So you can see the power moves it overall up slightly, and the relative difference between the unlensed and lensed CLTT also has this difference introduced due to this feature between the lensing contribution. So now if we do a reconstruction based on this data, so here we plot 4 possibilities. So here in the case of the unlensed CLTT, which is the ideal case, so what we do is we see that we can reconstruct the PK feature almost exactly accurately. Now if you don't, generally when you get the data, you get the lensed temperature power spectrum. You don't get the unlensed one. So if you don't consider lensing at all, you simply go for let's get PK from the lensed temperature power spectrum while pretending that the lensing is not there. This is what happens. So you get this bump, but then you get these spurious features superimposed on top of it because of the lensing contribution. As I mentioned earlier, the template method in which you assume a power law template for lensing and subtract it from the data. So if you follow that approach, you get something like this. So your spurious features have gone down significantly. Yeah, it has gone down significantly, but as you can see, it's still there, right? So if you have very precise data, you would get these spurious features, and you might say that, okay, I have features in PK which don't really exist. But for the iterative method that we have implemented, this is what you get, which is almost exactly accurate to the unlensed ideal case if you have unlensed data. So this is where the reconstructions, our algorithm stands. We significantly, improve the PK reconstruction, and no matter what physics you're going for, having an accurate, unbiased reconstruction estimator is always important. So this can be used in any other case which also, follows this kind of data modeling. There is a relative error between the reconstructions obtained earlier. This is when you don't correct for lensing. This yellow is when you correct it using a template, and this blue is when you do the iterative method that we showed, which is a significant improvement. We also do the same thing all over again with realization, the cosmic variance error bar limited this fluctuation, realizations, and you get the same thing all over again. We bin this to reduce these cosmic variance error bar induced fluctuations, and you can see again that the same reconstruction is improved even with considering realization noise. And we do this all over again for another kind of feature, which is more likely we already can rule out such bump-like features with current data. So this is more within the bounds of existing data. Such features may or may not exist, and better precision would be able to distinguish even these. So for features like this also, you can see our iterative reconstruction does produce improvement. So this is without considering lensing at all. The yellow is when you do a template correction, and the blue is an iterative correction. So you can see at every point, even though it's not perfect, it does reduce the biases in the reconstruction. So, and this is the data that was used, so it's out of order. So yeah, it concludes the talk. These are the conclusions. We can use Richardson-Lucy on CL55 data as an independent data source for constraining PK in a free-form manner. And with a sparsity algorithm that can help you gauge how robust the features you get are in your PK, if they're spurious or real. And we also provide this non-linear correction, iterative lensing correction in the Richardson-Lucy algorithm, which can significantly de-bias assumptions while correcting for lensing. So, thank you.
Time for some questions.
Can you possibly detect this weak lensing defect in the measure observed power spectrum?
Could you, in the power spectrum as well?
The observed power spectrum, can you possibly detect the effect of weak lensing? What is the magnitude of the effect?
Yeah, so weak lensing is detectable like from the temperature and isotropy map itself.
Right. But you said I couldn't get what is the magnitude of the effect? What percentage?
Okay, so it's at very small scales at around L of 2 to 3,000.
Yeah.
It goes up to as much as 10%.
10%.
10% of the underlying power spectrum. That's the higher part. So the higher in L you go, the smaller the scale, the more weak lensing dominates. At very high L of 5,000, 6,000, actually that's the dominant. Correct.
So are you saying at the moment the measurements are not sensitive enough to detect this?
No, so weak lensing has been detected. But in this context, so there are two things. So one for the CL55 power spectrum. So that currently has pretty high error bars.
Okay, that's what I meant. Yeah. So the moment it's
So the moment more it improves, so your peak reconstruction error bars will go down significantly, and that will be comparable to CLTT. And for CLTT weak lensing as well, the temperature sector, is that, so I showed you that bias while accounting for lensing. So if once the error bars improve even more, even for polarization and other data sectors, what will happen is that template-based accounting will no longer be optimal in some sense. So you would want to have this kind of iterative correction, which makes it accurate, more accurate.
Hi. Just a question on the perturbations that you had on the power spectrum. So basically, the motivation of those perturbations, does it come from, say, some inflationary models? Or what basically motivates doing those perturbations that were done?
So you're talking about these kind of things that we put in this analysis. Yeah. Okay, so these are not really motivated from a particular model, like physical model of inflation. These are more of trying to see how the estimator behaves. So this is like a smooth bump, and the other one was like a wave packet, like it's more high frequency. So just to see how the reconstruction works in either case. Now this is completely unmotivated, but this kind of feature, this has been studied already. So there are recent papers by Dheeraj Hazra and others, which do this kind of, which have predicted such features. And so the goal in some sense was also to say that this can help constrain such features better eventually.
Plant collaboration itself
Yeah.
does have
Okay.
sections devoted to local
Right. Yeah.
The features are so strong and sharp you are able to reconstruct them.
Yeah.
I think if there was something which was shallower and
Yeah.
broader,
Hmm.
how is this situation?
So if they're shallow and broader, so this kind of case, which is just a smooth, simulation, it will be able to reconstruct. But the issue is that you also have associated error bars in actual, observations. So if it's a very weak feature, or a very smooth and shallow feature, what will happen is you can't really say, given the error bars, if it's there or not. But in principle, it can reconstruct. So smooth and shallow features. So, related to that is these plots. So here the issue is actually if it's very high frequency. For example, the CL55 kernel can easily reconstruct smooth and shallow features because the kernel itself is fairly smooth. But so CL55 will not be very good at reconstructing spiky and fine features because they'll get washed out. Now CLTT can do both because as you see the support of the kernel is all the way from 2⁻⁻⁴ to 0.2 of K, like the megaparsec inverse, and it's quite jagged as well. So CLTT is good at reconstructing any kind of feature, and CL55 is only good at smooth and shallow features, smooth or broad features. And as to whether you can detect them depends on your precision of the data. So as you recall, this kind of error bar. So this is cosmic variance limited. If a feature is smaller than this, you'll never be able to get it. If it's above, you'll be able to.
Yeah, just a curiosity question. So at these wavelengths where you're observing, what is, lensing will be more serious for shorter wavelengths, right? And it'll keep on the effect of bending of light will decrease with as the wavelengths go longer. So the question is, at these wavelengths, how much is actually the angular correction that you expect through this thing? I didn't get that from the...
Which as in...
So you're talking about lensing of the cosmic microwave background.
Yeah.
Now this is going to be in some 50 to 60 gig or something is going to be where you're observing, right? Sorry? Is it achromatic? Oh, it's not like optical lensing at all.
Oh, you're talking about the photon frequency.
Is there an easy way to see why?
You're talking about the...
I see. So all light, it says velocity of light and you are... Oh, okay, fine, sorry. Okay. So I missed an important part in gravitational lensing. I'm very educated.
So let's send the speaker. So our next speaker is Anirban Datta, and he will talk on cataclysmic variable sources.
Good morning. So I will talk about the cataclysmic variable sources and their X-ray properties. So what are these sources actually? So these are why the cataclysmic. So these sources were observed